Okay, so you can see my screen, right?
Yeah.
Yes.
Cool, thanks. So in this section, we'll look at various methods of evaluating key phrase identification strategies and the data sets for benchmarking the methods. So before before we dive into the actual methods and talk about how their performances are, it would be nice to actually look at some of these existing techniques. Now, if you look at this slide, these are some of the most common strategies of evaluating key phrases, and the automated strategies are the most popular amongst them. Most of the works report their results on actual matching of the predicted key phrases with the goal key phrases in the ground truth. However, there are some efforts to come up with metrics that can take into account partial matching. Sometimes the key phrases are extracted for a specific downstream task, such as topic classification or text categorization. And in these cases, it is a common practice to evaluate the effectiveness of the key phrase extraction strategy based on the evaluation metric suitable for that downstream task. Human evaluations are very rare due to a lot of subjectivity and, of course, cost. So we'll look at all these issues more closely as we move forward. Now, here are some of the metrics used for evaluating key phrases. F1 at K is the most popular amongst the ranking-based key phrase extraction methods, which are traditionally the more popular ones. Simple precision recall and F1 measures are used for key phrase extraction when considered as a sequence leveling task. F1 at O and M are mostly popular in the area of key phrase generation. Now let's understand how each of these work. So given this example, so we can see an input document as shown in the slide with gold or the ground truth key phrases highlighted in it. So we have input document, and the idea is to predict key phrases and evaluate against the ground truth phrases given to us. So precision recall and F1 at K is calculated by considering the top K key phrases predicted by the model. This is pretty straightforward. So if you look at some of the benchmark data sets, however, we will find that there are basically we'll find that there's a high variance in the number of ground truth phrases. And often we set the value of K in the range between the number of predicted key phrases and number of goal key phrases, which means recall at K and F1 at K can then never be 1. So a simple solution could be to set K as a variable number, which makes it dependent on that specific data example that we are processing. And F1 at M and F1 at O were proposed exactly to take this into consideration. So for calculating, so suppose precision at M is always taken to be as a number of predicted phrases. So if the model predicts 10 key phrases, we take 10 in the denominator, and the denominator is completely determined by how many key phrases are predicted by the model. While calculating recall, we still consider the number of ground truth phrases in the denominator. And then F1 at M is calculated as usual. So in the example shown over here, M is equal to 15. And all the key phrases which are underlined are actually calculated to, are actually taken into consideration for calculating precision recall and F1 at M. Now for calculating precision at O, it is always taken, so the O is taken to be as the number of phrases in the ground truth. Now, as can be seen in this example, the number of phrases in the ground truth are 9. And so when doing our calculations, although CCD cameras and parallel cameras, they're both correctly predicted key phrases provided by the model, yet we skip them as we only consider the top O, or in this case, top 9. And in these phrases did not fall within that range. So these are some of the interesting facts about F1M and F1 at O, which explains why they are so useful. So F1 at M is equal to F1 at O when number of predicted key phrases is equal to the number of ground truth key phrases. So intuitively, at M and at O penalizes the cases where the number of predicted phrases and the goal phrases mismatch. A model predicts many bad phrases, you get a poor F1 at M. And then if the model is very conservative and ends up predicting few good phrases, only few good phrases, then you get a poor F1 at O. And this also accounts for the variable number of phrases for each document. And now models can achieve the maximum F1 score of 1 as well. Now this shows the usual precision recall and F1 scores. This is popularly, and this is basically very same as F1 at M. This is popularly used when key phrase extraction is treated as a sequence leveling or token classification task, as during that time it is often difficult to calculate the confidence score for each key phrase by adding together the scores for its component tokens or words whenever the key phrases are multi-word phrases. This does not allow us to come up with top K key phrases. So the normal precision recall and F1 measures are the way to go, where we take into account all the predicted phrases during the calculation. Now let's look at some of the issues with actual matching. So if you look at the predicted key phrases and compare them with the golden key phrases one by one, you will easily notice that some of the predicted key phrases looks right and can be easily considered as a good key phrase. For example, if you look at the phrase bridge, crack, inspection process, then mobile manipulator imaging system, you'll feel that in fact, it's a better key phrase than what has been given in the ground truth. But still, due to the actual matching criteria, you know, these phrases were not considered correct. And this is often a problem which leads to very low scores using the automated metrics. And these errors are caused by three most common reasons. One of them is the semantic variations. So here, 4-axis manipulator and 4-axis manipulator system are semantically same, yet they are considered different during the evaluation process. Then let's look at another type of error, which is overlapping phrases. So let's take the example of mobile manipulator imaging system. We can see that it has large overlap with two of the phrases in the ground truth. One of them is mobile manipulator and then imaging system. Then morphological variants, and these are caused by simple variations. For example, in the predicted key phrases, we have parallel cameras versus parallel camera in the ground truth. So it's just the S which comes on the way. And it is a common practice actually to stem these key phrases um, in order to address these morphological variations during the actual matching evaluation. So all of this led to the idea of partial matching. So partial matching scheme was proposed by the referred work, which takes into account all the variations as discussed in the previous slide, except the semantic variations. So the overlapping phrases are taken care by the include and the part of. So include is defined when extracted key phrases includes the gold key phrase. And part of is defined when extracted key phrases is a part of golden key phrases. And they also take care of morphological variants. Now, finally, they propose the R precision measure, which takes into account both the actual and partial matches. So they took the partial matches and got them evaluated by humans and found that the majority of the humans agreed in matching the morphological variants, but had issues with the part of variants. Several other evaluation metrics have also been used depending on the use case for which the key phrases are being extracted for. And some of these are very popular in the information retrieval community, such as mean average precision, mean reciprocal rank, binary preference measure. Even summarization metrics have been also used for accounting for near misses. Now, when it comes to data, two of the most important things that one needs to make sure is how to collect them and how to annotate them. So for the key phrase identification tasks, most of the popular benchmark datasets comes from the scientific domain in the form of research articles in different subjects along with their author assigned key phrases. Then there are a couple of datasets in the news domain which has news articles along with key phrases either assigned by the readers or professional editors. And then there are very few datasets from the web domain with key phrases assigned by the readers of the document. And this space is pretty much dominated by scientific domain as document key phrase pairs are readily available. When it comes to annotating these documents, there are three main practices. The key phrases are either annotated by the authors themselves or the readers who are sometimes asked to annotate them as annotators, professional indexers, or editors. Now, these annotations are really challenging. Unfortunately, there are no proper annotation guidelines, and if they exist, they're very domain and problem dependent. So here is an example which attempts to provide proper guideline to the annotators. However, as you might notice that they only provide a short definition of what a key phrase is, and then they talk about how one should go about selecting them. Now, this is completely dependent on the annotators to understand and perceive the document, and it is natural that each of them will have very different ways to perceive the same thing. And this was also intended as this pretty much mimics a real life situation. So as expected, this resulted in very low agreements between the annotators, which is very common in the key phrase world. Now, each of the annotation process comes with their unique challenges. The fact that annotation could be subjective exists in all of them. But let's look at some of the unique challenges that exist in each one of them. For author-assigned key phrases, there is an intent bias. This is related to the intent of the author behind annotating the key phrases. For an author, the main aim is to choose the key phrases that will make his work more discoverable and raise awareness of their work. This often leads to repetitive key phrase selections. And this also leads to choosing of more generic and abstractive key phrases. The author is also more motivated to choose a more exhaustive list of key phrases and can easily compromise on specificity over exhaustivity. The reader assigned key phrases comes with their own issues. Generally, the readers lack the expertise on the topic of the document in compared to the authors, which often leads to lower quality in the choice of key phrases. They also tend to choose more extractive key phrases and also more specific key phrases. The agreement scores between the readers are generally very low. This is primarily because no two reader would choose the same set of key phrases, and the choices would fully depend on the reader's background, expertise, and perspective of reading the given document. The professional indexers or editors are supposed to choose higher quality key phrases than the authors or the readers. But then this process also has limitations. The primary limitation is that the key phrases in this case are mostly selected from a controlled vocabulary. And this controlled vocabulary completely depends on the quality of the thesaurus and how the vocabulary looks like, whether they aim at choosing more generic or more specific key phrases to they correctly handle new topics and events, etc. Now, these are some of the most popular benchmark datasets in the scientific domain. Most of them are just abstracts, and those which contain full text are very small in size. KP20K is a widely used dataset due to its size, and it often is the choice for key phrase generation. These are the datasets available for news domain and the web domain. KP Times is the only large dataset in the news domain. OpenKP is a very interesting dataset which was released by Microsoft. This is the only dataset that allows to try out key phrase extraction in the wild, as it is open domain and consists of text collected from different web pages, which is indexed by Bing search engine. It also has visual features, which makes it also a multimodal dataset. Now, these are some of the challenges in the dataset world. One of them is language coverage. So there are hardly datasets outside English language, which makes it very hard to train multilingual key phrase extraction models. Second is domain coverage. As already said earlier, most of the data sets are in scientific domain. So we need more data sets in other domains, for example, legal, financial, then lack of large data sets on long documents. So most of the large data sets contain short abstracts, which is not we often deal with in the real world. And this has also skewed the research community to come with the methods that are most suitable for short documents. There's certainly a need to develop large data sets containing long documents spanning multiple pages. So lastly, we hardly have data sets for performing key phrase extraction in the wild. So OpenKP is the only data set that to some extent attempts to solve this issue. So more efforts certainly needs to be made in this area. Now, the lack of large data sets with long documents made us create a new data set by mapping the abstracts in KP20K and OHGKX corpus to the original full articles which we obtained from the S2ORC corpus shared by Allen AI. So we created LDKP3K and LDKP10K data sets that are available in small, medium, and large sizes along with all the metadata. The dataset has representation across multiple domains, and we also made efforts to make most of the popular datasets available in the Hugging Face Hub so that you can just write a few lines of code and download them in your laptop. Thank you. Next, I'll hand over to Florian to go through the traditional methods for key phrase extraction. Thanks.